Pascal's law, and we're saying Pascal's law and pressure. Well, just from the diagram, you can see below the picture, it already gives you a glimpse of where we expect to apply this. Of course, it's not limited to that. When you go to those Maway Bridge, if you're using a hydraulic jack, it's all Pascal's law at work. Now we need to understand it and also do some calculations, see how people come up with the capacities of those, so that in case you find yourself working in that place, you know when equipment is malfunctioning. So we're saying that Pascal's law states that the pressure applied anywhere in a confined incompressible fluid is transmitted equally in all directions throughout the fluid. That's what it tries to mean. Then the other version is that the pressure in a confined incompressible fluid at rest is evenly distributed in all directions. When we say all directions, we're trying to say that in all the planes, it could be the x-axis or the x-plane, the y, and the z. The pressure that is distributed is equal in all those. We'll see how this is done in practice when we sample an equation. What about pressure? Well, pressure is where sometimes people even bring up a debate. Is it pressure you're talking about, or maybe you're talking about stress? Well, it's the application that varies or that differs, but the effect is very similar. So in this case, even the definition is one and the same. So we're saying pressure is still the force per unit area, meaning P is equal to F over A. Pressure is force divided by area. But remember, the hydrostatic pressure is also important. Hydrostatic pressure coming up as a result of fluid being at rest is given by the product of specific weights and the height. Straight away, let's pick up an example. We've been given a hydraulic jack, which has a ram of 200 millimeters diameter, and then it's also coming with a plunger of diameter 20 millimeters. We'll soon understand what we mean by ram and plunger. Now, if a force of 200 newtons is applied on the plunger, determine the load lifted on the ram. That's what our headache is for now. So straight away, let's pick up the data. The first thing we've been given is the diameter of the ram, which is the bigger cylinder. Now, from this same diameter, you should be able to find the area, that is the cross-sectional area. And remember the formula we've been using, is pi d squared over 4. This time, to differentiate the smaller diameter from the bigger one, we're using capital D for the big diameter, which is for the ram. Then the other small d is for the smaller diameter. So pi times 0.2 squared over 4, and that's what you get. Then the smaller one is 20 millimeters. To get it to meters, you divide by 1,000. That's how come we even got this other number here. When you divide this by 1,000, you get 0.02 meters. Take it through the calculation, pi d squared over 4 is pi times 0.02 squared divided by 4. And this is the answer that you are going to get. You can always try it out in your calculator to give you the answer you have on the other end. What other information do we have? We also have the force acting on the plunger. We're using letter F to represent it. Now, this whole thing doesn't make sense if we were to just leave it like that. We need to take a step further. Try to understand in pictorial form. Of course, that will help us to find the load lifted on the ram. Now, here's our diagram. This is the plunger side. and this is our ram. Inside here, all this up to the other side, you have your liquid. And you have pressure 1 on this side and pressure 2 on the other end. So applying Pascal's law means that the pressure on this side is equal to the pressure on the other end, because this is a confined liquid, or rather, they are at the same level. If they are not at the same level, then it means we also bring in the effect of hydrostatic pressure. It also has to be accounted for. And we'll have an example that will help us to understand how you can handle such a situation. So this is our force acting on the smaller cylinder, which is the one we call the plunger. And the load acting on the bigger one, we don't know how much it is. That's the one we're looking for. So we have the ram and the plunger. But just like these mechanisms, in between these two cylinders there, you may have valves, could be non-return valves, pressure relief valves, name them. But when it comes to the capacities and how the loads will behave, that's how we analyze the principle without beating about the bush. Now let's try the working. So load over area. Here we are saying the formula for pressure is simply force over area. So on the ram side, the load acting on the ram divided by the total area of the ram. That gives us the pressure on the ram. In other words, we said this is like our P1 on the plunger side, and the other one is our P2. And as we are applying Pascal's law, we are saying they are the same because they are at the same level. And expanding these, that's what we have below there. Force over area. Instead of saying force, we are saying load because it's a bigger one. Which area? We're using capital A to represent the bigger area, which is for the ram. Next, we make F the subject of the formula. We multiply both sides by A. So here we can decide to multiply by A, and on the other side we do the same. Or rather, we're looking for the load, so it's the bigger A. And even on the other side, we multiply by A. With this, it means you can cancel that one, but here things remain. So that's why we have F multiplied by A over small a. What is our next step? Well, it's just about substituting. We already have the F. We're given that the force was 200 newtons. The bigger area was 0.03142. Then the smaller one for the plunger, it was 3.142 multiplied by 10 to the negative 2 square meters. Now, what about the brand of your calculator you're using? Just enter these values into that calculator. You should be able to find this value here, 19,987.269. If it does not give you that number, you're free to alert me so that we continue refining our work there. So let me just simplify it again. Here we're saying that we're applying Pascal's law. The two sides, the ram and the cylinder, are at the same level. And since they're at the same level, it means pressure 1 and pressure 2, they are the same. If they are not at the same level, we'll find example number 2, which will handle that case. And the formula for pressure is force over area. In this case, for the bigger one, it's load over the big area. We used capital A to represent it. As for the smaller one, on the plunger side, it's F over the small area, where we use small letter A. The next part is just to make load the subject of the formula, And that requires you now to multiply both sides by A, which is the area. So multiply by A this side and multiply by A on the other side. Cancel them. And that's what you have, F by A over small a. And what you see below here is pure substitution, and your calculator dances from there, bringing us down to this answer there. Now, let's try a totally different, or rather an example that makes things a bit interesting. Here, the scenario is that we have a plunger whose diameter is 30 millimeters, and the ram is having a diameter of 210 millimeters. The ram is 50 millimeters above the plunger. See the difference? The things are not at the same level like we had in the first example. And the other thing is also that we are not using, we've also been introduced to this newcomer here, which we saw in the previous lesson. 0.9 is our specific gravity. We need to use it to find specific weight. The load given is 4 kilonewtons. A kilo represents 1,000. So that's why we can safely say it's 4,000 newtons. So the small diameter D for the plunger is 0.03. The height, difference height, which is being used now this time for the ram, is 0.05 meters. That's what you get when you convert the 50 millimeters to meters. Going back to the formula, pi d squared over 4 gives us pi times 0.03 squared over 4. That's your answer. Second one, for the ram, we have the diameter of 210 millimeters. If you divide by 1,000, you get 0.21. Now this means that your area A is pi times 0.21 squared over 4, and you get 0.03464. Load given is 4,000 newtons or 4 kilonewtons. What do we want? We want the force applied on the plunger, F. Now, one last item for our data is that we already have 0.9, which is the specific gravity. But specific gravity on its own is not very useful for this working. So we need to find the specific weight for this one. Now, if you go back, your specific gravity is the ratio between specific weight of a substance, in this case, which is a fluid, divided by specific weight of pure water. Now, interestingly, here, the value we have is 0.9, 0.9. But on the other side, we have the specific weight that we're looking for on top of the fluid, then divided by the specific weight for pure water. This is the one we said for pure water. The specific weight is 9,810. Where does this number come from? This one comes from simply getting the density of pure water, which is 1,000. Then you convert it to specific weight, meaning you multiply it by G, which is 9.81. 9.8. Forgive my handwriting there. Writing using a mouse can be funny. So when you get this 1,000 by 9.81, what you get is 9,810. Now this scenario is what we reach here. Make this the subject of the formula. All you need is just to cross multiply. So 0.9 multiplied by 9,810. What is your value? It gives you 8,829. You can take your time to go back to the introduction to fluid mechanics where we discussed the fluid properties. It will help you to refresh and understand these properties even better. Now, this is the scenario we're talking about. The ram is at that height. The plunger is below. So we're saying the ram is above, meaning the ram is on top. The plunger is below. By how much? The ram has been raised up by 50 millimeters. You convert 50 millimeters, you have 0.05. That's the one we've put there. So if you look at this, it means that the pressure we are calling P1, this is not equal to this because the height has been disturbed. They are no longer at the same level. You have to take care of this fluid in between here, this one. And how do you find the pressure now as a result of this fluid filling up this level XX? Very simple. We just go back to the formula we talked about, hydrostatic pressure, multiply the specific weight by the height. So which means that we'll have F over A on this side being equal to load over A on that other side. Then we also add this one, meaning the total pressure acting on this surface, which is at the same level with the plunger, is specific weight multiplied by the height added to pressure 2, which is load over capital A. Load over capital area. Okay, then we can always finish it up if you want. Handwriting is improving. Yeah, it looks scary for now. So that's load over capital A. So this one is supposed to be equal to the other pressure there, which is F over A. And we're saying it is F applied force over small letter A, just like that. Like I said, please forgive my handwriting. We'll get better as we go. So in the working, applying Pascal's law, that's what we have. Load over area, we are adding the hydrostatic pressure because it is raised at that height. This one is at the same level with this summation here. So this remains F over A. Now let me take you back to the diagram. You always add this to the one which is up. If it was the plunger which was up there and this one is below, then this specific weight by height was supposed to be added to this side instead of the other side. So that's the equation we have there. And our part now is just to make F the subject of the formula. There you are. But like I might have emphasized, you do not need to suffer this way. You can just go straight and substitute all of them. To even make your work easier, because after substituting here, you have one complete number. Here you get a number, there you get a number, and it will be there. You just go multiply and you are done. Because here you have a complete number after you're working. Either way, algebra has a lot of choices. What I put up here is just one route you can decide to take. So let's go ahead and substitute. We're saying it's 4,000 divided by the area, the bigger one. Then we are adding 8,829, the specific weight just as we found it. The height given is 0.05. So we multiply by that same 0.05. Outside, we have the smaller area, which is 7.069 multiplied by 10 to the negative 4. Now, once again, don't worry about the kind of calculator you use. Even if you use this one, which you go on WhatsApp and you run out of bundles, then it gives you an error. As long as it's a scientific calculator, it should be able to bring you all of those. It gives you that. Then finally, 81.94. 81.94. If my calculator went on some holiday, please feel free to correct me. So that's how you handle a situation where the two sides of the cylinder are not at the same level. You also make sure balance it out with this effect of hydrostatic pressure. And then you can make F the subject. Making F the subject of your formula depends on how you prefer to go about it. That is your exercise. As you've always demanded, I've added all the answers so that as you try out, you can see where you are going wrong, and you can even make corrections, making sure that you progress and get there. So try them out. See if you get the same answers. If not, once again, you're free to communicate. Thank you very much. Our lesson will end here for now, and we'll link up in the next lesson. This time around, I think we'll try to talk about Archimedes' principle, which is the one that anchors flotation and issues of buoyancy. So get there. Until we meet, thanks a lot.